Why is quantum standardization so hard? Imagine trying to get a group of people to agree on a game they've never played before. Now, picture that game involves tiny particles that behave in strange ways. That's what makes standardizing quantum technology so tricky. First, quantum systems depend on qubits, which are extremely sensitive to their surroundings. Even a tiny heat change or electromagnetic interference can cause errors. Fixing these errors requires complex techniques called error correction, which often needs dozens or hundreds of physical qubits to make one reliable logical qubit. This makes setting consistent standards for performance and reliability very difficult. Next, there are many different types of qubits, like superconducting qubits, ion traps, photonic qubits, neutral atoms, and topological qubits. Each has its own strengths and weaknesses. Since no one technology has become the clear leader, creating standards for hardware interfaces and performance metrics is complicated. Plus, these technologies are still evolving fast, so standards could become outdated quickly. Scaling quantum computers is another challenge. Today's quantum machines have only a few dozen qubits, but future systems might need thousands. As the number of qubits grows, controlling and shielding each one becomes exponentially harder. This makes it uncertain what performance levels or system designs will be common in the near future, complicating standardization efforts. Quantum computers will not replace classical computers but will work alongside them. This hybrid setup requires standards for how they communicate, share data, and stay secure. Defining these rules is tough because quantum and classical systems operate very differently. International cooperation is also a major hurdle. Different countries and organizations are developing quantum tech independently. Without working together, they risk creating incompatible standards, which could cause problems for global applications like secure communication or cryptography. Software is another piece of the puzzle. Quantum programming languages, algorithms, and tools are still in early stages. As new algorithms are discovered and software evolves rapidly, setting universal standards becomes a moving target. Finally, security and performance often trade off in quantum applications. For example, some quantum-resistant cryptography algorithms requiring heavy computation, which might slow down real-time systems like autonomous vehicles. Balancing these needs makes it harder to create one-size-fits-all standards. All these factors mean that preparing for a future with quantum technology requires flexible, collaborative, and ongoing efforts. Countries and industries need to work together, share knowledge, and develop adaptable standards that can evolve as the technology matures. This way, society can benefit from quantum advances while minimizing risks and confusion.